Okay, I think everything is all set up. Welcome to the Monday seminar. Absolutely fabulous to see so many people, so many familiar faces, as well as new people. This seminar has been going on for quite a while now, and the reason is because we've been lucky to get people like Felix Waldhauser to agree to put together a really high-end talk. And so we are going to be enjoying listening to that and participating in discussion over the next hour or so. Typical talk length is around 60 minutes. We ask people to mute during the talk, but encourage people to unmute and interrupt with points of clarification, small questions. Ask something to help Felix remember that he's not just talking to his screen. And then we have an extended discussion and question and answer period at the end, during which I will repeatedly invite everyone to participate in. So especially for early career grad students and things, I can recommend to you right now, you get a piece of paper, make some notes of things that you'd like to discuss and ask questions about. Okay, nothing else from me. Felix, thank you very much for being here, and please take things away.
Oops. Okay. Thanks, Chris. And thanks for inviting me.
Good morning, Paul.
Thanks for inviting me to this session. I realize I have 60 minutes. That I hope I don't go over 60 minutes. But the title, and I'm sorry for the title, is a somewhat generic title, but putting the talk together, I realized that maybe a new generation is a little bit too bold or too ambitious, because it's essentially what's going on now is the next step in the evolution of how we create catalogs and then also deal with catalogs. I'd like to acknowledge, so this talk is going to be work that a lot of colleagues and people worked on, and I want to mention them right at the beginning. So the Kai-Wen Wang, who was a postdoc here and is now at the China Academy of Science in Beijing. Eric Bozé, who is still a postdoc here, who gave a talk a couple of weeks ago in this session. Then David Schaff at Lamont, Ben Holtzman, Yenjo Tan, who was a student here and a postdoc at Stanford, and he's now at the Chinese Academy of the Chinese University in Hong Kong. Then Theresa Savi, who was a student here, is now a Mendenhall Hall at the USGS, and Fola Kolawole, who is here at Lamont, a structural geologist. And then also members from the SCOPE team, and I will mention them during the talk, and the Axial team, the Axial Seamount monitoring team. What I'm going to do today is first I'm going to touch on progress that we collectively make in large-scale, high-precision, deep magnitude earthquake catalog production, and then in the context of seismic monitoring when we do that in near real time. And I think to summarize those new there isn't a day where we don't have a new catalog and new machine learning model. I think to summarize all this at the end, I think we can say that when we build catalog, the perfect is the evil of the good. Sometimes you want to make the perfect catalog, but it may be not even appropriate for what you want to actually study. And then the bad catalog is just evil, because especially if we don't know what's bad in the catalog. I will show examples from using those catalogs to infer fault structure and then geometry and mechanics during aftershock sequences. And the two examples I'm showing is Central Italy and then also New Jersey, which might surprise a few. And then I will touch on how we use existing high-precision catalogs to study repeating earthquakes and what they tell us about fault behavior in California And then I will end with our recent work in using machine learning to detect volcanic precursors and monitor them in real time. So in all those examples, and my aim is to highlight some of the pitfalls or some of the problems we have, and then some of the opportunities that we can take advantage of. I started with the very basics of how we detect and locate and then an earthquake and then monitor seismicity in general. So it all goes through a detection process and then the process of picking an arrival time, then associating those arrival times with earth event, seismic event, discriminate the event between from say blasts or explosions and earthquakes and other seismic events, and then locate the earthquake. And sometimes the discrimination part comes after we locate the earthquake. And then there's the add-on process of measuring relative arrival times on seismograms by cross-correlation, for example, and then relocating the earthquake with respect to the neighboring seismicity using those high-precision delay times. And then we can add another step, is template matching, is using those templates that we get from the existing catalog and search nearby continuous data streams and search continuous data streams for nearby events that have correlated seismograms. And so we have been doing this for many, many years and decades in some form or another. And then over the last couple of years, we have been the new tools were coming up that are based on machine learning tools, methods. And so the whole front end, the whole back end is going to be replaced with starting with the detection using those picks, manually picked arrival times as training data sets, and now easily detect future events or recover undetected events in the past continuous seismic waveforms. And then the same goes with arrival time picking and the association of those picks with seismic events, and the discrimination is now all taken over or added to the traditional methods of monitoring seismicity or building catalogs. And so, because machine learning detection recovers many previously undetected earthquakes, we're now dealing with catalogs that have hundreds of thousands, if not millions, of earthquakes. And here is just two examples from a machine learning or template matching catalog in Southern California, and the machine learning catalog from the Amatrice secret in Central Italy. And so we need ways to, or new ways to actually look at that data to make most out of all the effort that goes into getting establishing those catalogs. So a couple of years ago, we started a project we termed Scoped, which had the goal to combine data intensive tasks in seismology and compute intensive tasks in seismology to build a platform that can be accessed by the community to run this either in the cloud or on a supercomputer. And this is a project with Carl Tape in Fairbanks and Abreu in Colorado, Abreu Bostock in Colorado, Marine Denol at UW, myself at Lamont, and Ian Wang at TAC. And so this includes workflows that will use SpecFem and noise correlations and all the standard tools that we use in our own clusters, trying to make them available to the community. And And the Lamont part is generating workflows for the production of earthquake catalogs. And so you can see here, this is not complete. This has been I haven't updated that. But so this includes those various steps that I just mentioned, from detection, phase picking, association, and putting modules of standard software that we can then apply to the continuous waveforms. And it will be used for generating catalogs, but also for using those catalogs to analyze and then also discovery of new or hidden patterns. And it uses both machine learning, supervised and unsupervised, and just standard analysis tools, including kurtosis picking, etc., etc. And we can do that retroactive using millions of earthquakes, or then in real time, as I will show you later. And so the three catalogs I'll be showing examples of are shown here. One is California. That's our playground, or like training ground for developing new tools for many years, if not decades. And then we look at, I'm going to talk about Central Italy, the Amatrice sequence in 2016 and 17. And then I end with Axial Seamount, a volcano in the North Pacific. And you can see from those three catalogs, or three map views of catalogs, is that they span different scales. They go from hundreds of kilometers to tens of kilometers to kilometers. And they span, they include 1,000 stations in California, 100 plus stations in Central Italy, and then less than 10 stations at Axial. And they include millions of 1 million earthquake over 40 years in California. They include 1 million earthquake in 1 year in Central Italy, and 100,000 plus earthquakes in just days at Axial during an eruption. And so developing those catalogs all require different approaches, and that have the different problems given the high rate or high spatial density. So before I start looking at some of the results of those, or some of the special features in those catalogs, I wanted to go back and remind or correct some misconceptions that I have experienced over the last many years, especially with regard to relocation using cross-correlation data. And now that we have peaks that are more consistent and more numerous, that the relationship between the cross-correlation data and the peak data, I like to emphasize on that a little bit. So the correlation delay times are not better than peaks, and in various ways. So for example, you get two earthquakes here, the red dots. When you have a network on top of those earthquakes, you can pick those arrival times very accurately for stations that sit right on top of them. But for stations that are out at greater distances, you know, the noise increases, the signal to noise ratio increases. And so picking the onset will be a little bit more difficult. And when you correlate those events, the best correlation for that particular pair, you get at far distant stations, because the path outside the source region is identical. But you don't get any correlation measurements for stations that are right on top of the two events, because those paths travel different media. And so it's really the key is to combine those two, so that you have onset picks, that you have good picks for nearby station, and then you have the cross-correlation data when you go into the finer details of the structure, because the correlation data is of much higher precision typically. And so the key is to, in an iterative inversion, to dynamically weight those data. at each step of an iteration. This is summarized somewhere here, that this is actually a real example from the Nazca plate. You can see the you can a hint of the double seismic zone, the lower plane. Can you see my cursor or no? Okay.
Yeah, we see it quite well.
So you can see the lower plane and then the upper plane of the double seismic zone, where earthquakes correlate, shown in red here. And then the earthquakes that don't correlate, just linked by phase picks, are the ones in blue. And so after every iteration, the relative distances change, because we want to optimize that distance by optimizing the links. And so we're going to apply weights to those links as we go through each of those iterations. And so the key is to find the proper weighting scheme in order to minimize the residuals and to optimize the precision of the relative distances between the events. And so this interplay between PICs and cross collation data is important in understanding some of the figures I'm going to show in a bit. So more general, so when I say the evolution of catalogs, and one very nice demonstration of how those catalogs evolve is shown in Chiara Luce in 22. So he compiled all the catalogs that are available for the Amatrice sequence in 2016-17. So it's a sequence of 3 around magnitude 6 earthquakes over 1 year, which generated a lot of media response, of course, because they were very destructive. But it also generated a lot of data, and with the permanent station being augmented by the geological survey of the British Geological Survey. So around 130 stations recorded that sequence. And so the top left here, you see the routine production catalog from the INGB with 70,000 earthquakes produced in real time. And then the next, so we named them Cat 0 to Cat 5 right now. So Cat 0 was the real-time catalog. Cat 1 was a reanalysis of the reviewed pics of that data, and then in Michele 2020, there was a cross-correlation and relocation analysis of the best earthquakes in that catalog of Chiara Luce. And then Spalarossa 2020 had a catalog with of 500,000 earthquakes, where he went back to the continuous data and applied pickers, improved automatic pickers, and then located them with non-lin locking grid search. And then the follow-up catalog is a relocated one based on cross-correlation data, generating about 500,000 earthquakes. And then the latest one is Yenjo's applying the PhaseNet to the continuous waveforms and generating a catalog of about 1 million earthquake over the 1 year period. So Cat 6 will be the next one that we're trying to set up, is correlating that catalog, that 1 million earthquake catalog, to get a precise delay times and then relocating them. And I guess Cat 7 will be applied template matching. So an easy way to see the evolution of the catalog is by looking at the frequency magnitude distribution. And you can see with each catalog we have a lower magnitude at detection threshold. Starting with a routine location at about 1.5, magnitude 1.5, all the way down to Cat 5, the machine learning one, which is below 0 at minus 1. And so on the right is a figure from Ian Joe's paper showing the in magenta the routine picks from the INGV, and then in black, underlying in black, the machine learning picks. And you can see that it pushes down the detection threshold by an order of magnitude. Now, when we look at the relocations of the machine learning picks, you can see extremely rich details in fault activation. So on the left, the Amatrice Visa sequences, and then on the right, Norcia and Compatosta. And you can see the details in individual faults, less so the details in the internal structure of the faults, because there's still some uncertainty in the picks compared to if you use cross-correlation data. But you can see the very small faults activated or reactivated on structures, inherited structures, and with the hypercenters outlining areas devoid of seismicity, simply because they ruptured. Now I'm gonna look at the CAT4, which includes cross-correlation data, the 500,000 catalog. And I'm going to focus on the Norcia event, which is right here. So here is a distribution of CAT4. The top, this is a cross-section looking onto the fault, looking east. And you can see the same structures as in CAT5, except that it has fewer events, and very likely it has fewer faults, smaller faults that are highlighted in the CAT5. At the bottom here you see the distribution of correlated earthquakes. Those are the earthquakes that have correlation measurements that presumably are on simpler faults rather than complicated faults. So on the right side, you see a map view of the correlation data, and one of the characteristics of this distribution is that we have correlated earthquakes, quite a few of them south of the Sibillini thrust, and then north of the Sibillini thrust, we have much fewer correlated events, and that's presumably or mainly due to complicated fault structure or fault segments or fault zones. So in the south, we know from Luisa's work on Aquila sequence that we have very simple faults, or very narrow and with high numbers of correlated earthquakes, and again beautiful images of fault zones. And this seems to be changing as we go north. So we're gonna look at the details, the structural details here at the Norcia event. And I'm going to zoom. Yes, so before I do that, but what we can do with the details in the seismicity is we can essentially isolate the main shock and immediate aftershocks, apply a principal component analysis to the hypocenters, and then define the active fault planes. And so this is a figure that on the left that shows the various active faults that were activated in the Norcia, Visa, and Amatrice, and then the detachment faults. And I'm going to show a zoom into this very area where the Mantmetore fault intersects the detachment fault here. And you see this is the Norcia earthquake that ruptured the Mantmetore normal fault. And at the bottom and at the intersection to the detachment, we see a very broad distribution of subparallel faults, which we interpret to be bookshelf structures that form from the shear movement on the detachment fault and the interaction with the normal fault. So we're seeing some of the details in those high resolution locations. And so presumably when we have the machine learning catalog relocated with correlation data, we would those details should emerge much more clearer, and we can explore those structures on other faults. So when we have the the fault plane, and we can compute the distance of the seismicity of the aftershocks from the fault plane, and we can map them out as a function of location. And you can see that what we see is that the faults are narrower in the south, we just realized by looking at the correlation data, and they broaden to the north, so showing an increased complexity from south to north, and a narrower distribution for the footwall as compared to the hanging wall, for example. So Campotosto is the one in the south in red, and then we go up to Norcia, which is in light blue over here. Oops. And so the damage zones are comparable to one with immature fault structure, as compared, for example, to the L'Aquila fault zone. We also can compare that to a study that Clément Perrin did a few years ago, looking at aftershock sequences in California and their fall off with distance from the fault after larger earthquakes, so including Parkfield, Morgan Hill, etc. And so the same thing here, the mature faults, like a Parkfield section of the San Andreas fault in dark red, the fall-off curve is much steeper, indicating a more mature fault segment compared to, for example, Landers, which has a more broad distribution. And so we can correlate those fault maturity and fall-off rate for earthquakes in aftershocks sequences. So moving to a different part, and one that we wouldn't really think of applying those advanced methods to build catalogs, is the eastern US, not a plate boundary, like a stable continental region. But last year we had a 4.8. I know for Californians that's no big deal, but it was a big deal here because it generated a record "Did you feel it?" report from the USGS. Mainly because it's close to New York City, but also because seismic waves propagate much easier in the east than in California, for example. And so this earthquake was only 65 kilometers from Manhattan, and caused remarkably little damage. So this is the only significant damage that we found is an old brick building. So we went out after the main shock on a Friday. We started deploying instruments on Sunday, and then we had the USGS deploying instruments on, I think, Tuesday, and then TextNet came a day later, and then Rutgers and Yale. And so we had a decent amount of instruments out there recording the aftershocks. And you can see the aftershocks decay rate in red. Those are decay rate from, in the blue histogram. That's the decay rate from the USGS location for detections. And then it picks up again once the instruments were deployed. And you can also see the media coverage is very short-lived. It's like a day or 2 or 3, and then the whole thing dies out. So Eric Jose looked at the data, got the continuous data streams from all the temporary stations that we deployed, applied his BPMF workflow, which he showed results a couple of weeks ago in this session, as he applied it to the Ridgecrest earthquake and found the strengthening tidal modulation of seismicity towards the Ridgecrest main shock. So anyway, he applied a tool that uses back projection, uses FaceNet to pick the arrivals, then uses template matching, cross correlation, and then we relocated the sequence using double differences. And the catalog that he produced over, I forgot, maybe 6 6 weeks or 7 weeks or 2 months, is at 2,000 aftershocks, as compared to the 200 aftershocks that were located by the USGS using both permanent and temporary stations. And the distribution of the aftershocks shown here on the left, the map view. Then this is a cross-section looking along the fault, shown as hypocenters. And then if you look at the density distribution, we see a very clean fault where most of the earthquakes occur at 45-degree dipping, south-east dipping fault that's striking almost south-north. The on-fault distribution of the aftershocks is shown on the right here. The main shock was shallow and then propagated downward, as according to a slip model from Won-Young Kim was helped build with Korean colleagues. And then the distribution surrounds essentially the slip area, with one interesting feature is that at the bottom right here, it essentially it must be stopped by some kind of barrier because it almost piles up the number of aftershocks. And so the geologic model that we think is applicable to this sequence is that it is on it's not the Ramapo fault. The Ramapo fault is the big fault that runs northwest, which is believed to have to be it's debatable whether it can actually generate magnitude 7. It could generate magnitude 7 or 8 just based on the length of the fault. But whether it's active or not is still it's still unclear. But this fault, this sequence here, occurred just to the south of it, but abutting what we think is at least a strand of the Ramapo fault. So there's an interesting sequence that we're trying to understand now, and it clearly shows that maybe it's not, the worry is not the magnitude 8 on the Ramapo fault, but even a magnitude 5 or 5.5 on one of those smaller faults acute to the Ramapo fault might cause a significant damage to the New York City metropolitan area. So I want to switch, and so those papers are out. They're in production with GRL. I think they have been in production with GRL now longer than it took Eric to build the catalog. So this just shows how advanced those tools are now at getting those catalogs and the information that we take from them as quick as possible. So I want to go look at some of the a different topic where we use those catalogs and the topic of repeating earthquakes. And the basis of our analysis for those repeating events, or finding those repeating events, is that the California catalog, that's cross-collation based double difference relocated catalog that we've been working on for many years, which we essentially use the Northern California routine catalog, correlate all pairs of earthquakes that we find within 10 kilometers or so, and then compute differential times. And you can see the latest update of that catalog we did in 21. It now has almost close to 8 billion correlation measurements that we can use to relocate the events. And then we relocate the entire catalog to get a high precision, high resolution earthquake catalog. And then we implement that new catalog in the real-time system that we have been running for many years now, and relocate each new earthquake with respect to the base catalog. And if so, this new catalog is all implemented in and available from here. And so that, just to point that out, that's the version that you get from Berkeley is still based on an old catalog, and so we have to update or make sure that future analysis will be done with the most recent version. Oops. So we are harnessing those 8 billion correlation measurements. So on the left side is a distribution of the correlated earthquakes in Northern California based on that database. And on the right is the plot that shows the fall off of the correlation coefficient as a function of distance between the hypocenters. And as you can expect, you have a very high correlation coefficients for very close events for the San Andreas fault, especially the creeping section up here. And then it decays for a place like the geothermal, the geysers geothermal field, where you have small faults and small faults and don't get the kind of length and smoothness of a creeping San Andreas fault. And so that fall off here is much faster, and then it peters out. And so we are focusing now on this very narrow zone where we have very close by hypocenters and very high cross-correlation coefficients. And that's where you expect to the repeating ends to sit, as we assume that they are collocated and have high correlation coefficients. So this is just a summary of, yes?
Hey, sorry, it's Chris. Can you go back? Are you always using about 3 or 4 seconds worth of data for the correlation?
1 second.
Ah, okay. So you just use
You mean the correlation window?
Yes.
Yes. So this data is based on 1 second p on the p, but I'll get to that. It's very short.
Thank you.
So it's a good point, because the shorter the window, the higher the correlation coefficient. So yes, so with this, that's why I'm putting in possibly repeating earthquakes. So this is going to be a large number of possibly repeating events. So just a quick review of repeating earthquakes, and this is a good figure from Uchida. You essentially have overlapping rupture areas for repeating events, assuming they rupture the same patch. You have very similar seismograms throughout the sequence. And then from that, you can get slip rates using an empirical relationship between moment and slip. Typically, they're thought to represent stock asperities on an otherwise creeping fault. And we can use them to understand or infer fault structure or fault behavior, and improve hazard assessment and earthquake forecasting. So an easy way a simple way to show the importance that we actually know where those events are is the safe or target repeaters. So you can see those are 3 individual sequences with repeating earthquakes, and they're all only separated by a few hundreds of meters, a few tens of meters at the source. And for example, on a cross section here, you see that we have they're actually not even on the same fault. So if you get slip rate estimates from those repeaters, you have to make sure that you account for the different strands. And once you resolve the spatial distribution, you get the temporal periodicity. And so we did that for the entire Northern California using a bottom-up approach, and that's where Chris's question comes in. So once we found that the potential repeaters based on a short window, we compute longer windows to make sure that the whole wave train is correlated. And then we select for similar magnitudes. We relocate the entire each sequence independently, and that gives us a catalog of over 7,000 sequences, with a total of 27,000 repeaters between 1984 and 2014. And then we compute additional measurements, including differential magnitudes, coefficient of variation, slip rates following Nadeau and Johnson. And so here I'll show on the right are 3 examples of what we find. So broadly, like end members. The easy ones, the collocated ones with high correlation coefficient. The overlapping ones, the messy ones that have no clear co-shared rupture patch. And then we have the problematic one, the nested ones, where we have apparently 3 sequences, but it's not clear what patch those sequences rupture. And just to go back to that complicated one here, so you can think of those sequences rupturing away from each other into separate patches or towards each other to host one patch only. Or you can play around with the stress drop and have them high stress drop, making them all individual patches, or a low stress drop and including everything in one patch. So in this sequence, maybe what's happening is that we have two sequences that are co-sharing a rupture patch, and then the red one, which is here over at the bottom left, is rupturing away from the patch. So taking those sequences apart for slip rate measurements is a tricky thing. So additional measurements here in the future will definitely be getting at directivity and then adding stress drop to get a sense of how big the rupture patches are. And there's been lots of research done on this. So on the left, there's in Uchida and Bergman's review paper, with a figure from Kim in 2016, you see that when you compute the slip models, then you see the peak slip areas overlap in this particular case for a park field. And so here you can be sure that they rupture the same fault patch. And then in this plot here, also from Uchida, it shows the distance between the events and the coherence between the signals, respective signals. And what you expect is you have a decay of the coherence with increasing distance. But what's interesting in those plots is that you actually have a broad distribution of coherence values, even for collocated earthquakes, depending on the stations that records the event. So you have to be very careful in making sure that if you have stations that correlate, that you actually kind of weight them or by quality weights. And then there's the big question whether, especially for slip rate estimates, whether those slip patches creep aseismically during the endoseismic period, or whether we actually release the whole moment from the slip patch in every signal in every repeat instance. So in our analysis of slip rates, we went back and just looked at the periodic ones. So the periodic, for example, here, that release moment and a periodic timescale. And what we use to characterize periodicity is the coefficient of variation. So periodic ones have a 0, and then very random ones have above 1, and then you have temporal clustering, for example, over here, where they repeat and then suddenly stop and then pick up again. Or you have piecewise periodic, where you have a repeating sequence, periodic, and then you have a transient disturbance from, for example, a nearby bigger earthquake, and then you recover the periodicity. So we have compiled a database of periodic repeaters, or semi-periodic or quasi-periodic repeaters. And this is the distribution. What you expect is you see them along the creeping section of the San Andreas Fault, but you also see them north on the San Andreas Fault in the Macama segments, for example, or in the Mendocino Triple Junction, and some in Long Valley. In general, they correlate with observed creep rate at the surface, but not always. For example, in the Bay Area, here at Golden Gate, you have a repeater. You have a repeater up here in Point Arena, and then just south of the Loma Prieta rupture zone. And so this is a use of the slip rates in central San Andreas fault, going from the creeping section of the San Andreas fault into the area where it sprays off the Calaveras fault and the Sargent fault. And if we plot those slip rates as a function of distance along the fault, so this is the San Andreas fault creeping here, we approach 20 millimeters per year at the peak, and then it starts to decay as we have subparallel fault strands with repeaters as well that seem to be creeping. So for example, the Pine Rock fault over here, or the San Benito fault over here, and it goes into the Calaveras fault over here, and then the Sargent fault over here. And so you can see when you sum up those slip rates, you get a very continuous increase in slip behavior of the San Andreas fault system. And then it decays once it goes into when the Calaveras starts moving into the Haver fault, where the Haver fault has a slip rate of about 10 millimeter per year. And so it's a very consistent slip partitioning from south to north, and that if you compare that to the use of 3 slip rates, that's much more rugged and inconsistent. We'll probably have to update that with the latest model. So those repeaters and the slip rates from repeaters are very useful in estimating slip rates of subparallel strands and then slip partitioning for hazards. Okay, I'm gonna go running out of time. And so maybe what I show here is when you plot, so some problem here is the large standard deviation of those slip rates for a given section. And so when we go back to the repeaters, for example, here we see that there's one missing. So this here is one missing. That's when the recurrence interval doesn't match up with the moment release. And so with Teresa Savi she used SpecUfX, which is an unsupervised machine learning tool, to, instead of looking at the short window cross correlation measurements, you do a global search on the fingerprints. The fingerprints are constructed from the spectrograms of each earthquake in the Northern California catalog, and then the dimension is reduced by non-negative matrix factorization and hidden Markov modeling. And so we can very easily compare those fingerprints on a global scale. And what she finds is more repeating events, for example, new repeating events over here, sequences, or she finds missing events in existing sequences, for example, over here. And then, so we can increase the resolution in our slip estimate on a certain fault. So we did that for a short segment on a creeping section just as a testing ground. And so the increased resolution in repeating earthquakes, the slip rates we get from them is shown here. And we can more clearly delineate the aseismic part and probably stock patches. So this is a study that we want to expand to the entire catalog of Northern California. And then we still need to go, that is just to find the potential ones, we still need to go back and constrain those repeaters. Okay, so and so the goal is to, within our real-time system, to plug in the repeater catalog and then have that being updated automatically as part of the monitoring process. So the last topic I want to touch here is one of the most advanced catalog production work pipeline we have is in Axial Seamount in the North Pacific. It's a volcano that's supposed to, it's about to, we think it should be blowing up or erupting in the next, between now and the next a year from now. We said that like maybe 2 years ago. So I hope it's not like a park field thing. Anyway, so there's a very advanced cabled network, OOI network on the volcano. It has seismometers and all kinds of other instruments, deformation, and cameras at some point. And there also has been very high resolution MCS data acquired. And we have a very good understanding of where the magma chamber is at the top and the magma system looks like. I want to focus on the seismic data. The seismic data. So here is a map of the station. The stations are here in yellow. There are only 7 stations that are cabled to the shore and send data in real time. The array captured the 2015 eruption, which the results are shown here. It shows, part of the ring fault system. Over here is a cross section. It's right at top on top of the AMC, and with a higher resolution catalog, we can find all the different individual faults, including ring fault system and the dikes, and also some slip faults that are subparallel to the ridge. So the focus here is on the kind of data that these OBSs record is very complex. So besides earthquakes, they record all kind of whale calls. So anything from fin whale, sei whale, blue whales, and then they record the impulsive seafloor events that are events that are generated from hot lava reaching the cold water. They get reflected from the sea surface and then recorded at the OBS. And here's an example of that. So the first reflection, second reflection, and then third reflection. And so we can actually use those seafloor pops, or you want to know magma pops, to locate and time the lava flow pattern. This is not for the EPR, done by Yan Zhou, clearly indicates the overlapping lava pop, the impulsive seafloor events overlapping with the mapped lava flow from ROV. But in addition to the mapped lava flow from ROV, we find actually the temporal evolution of the lava flow. And so in order to process the data, there's work that Kai Wen worked on in her postdoc year here, is that she used the continuous data stream, used FaceNet to pick, gamma to associate, then use an unsupervised event discrimination tool, the SpecUFX that Teresa used, to discriminate between all the different seismic events. And then got the initial location using grid search, and then the correlation, then the relocation, and then all the way to running this whole thing in real time. And so the discrimination part is interesting because again, spectrograms get converted into fingerprints and then clustered, and the clustering showed various seismic events, from earthquakes to the whales to the impulsive seafloor events. But most interestingly, it showed at 2 clusters in the earthquake segment. Is like the regular earthquakes, and then what we call the mixed frequency earthquakes, which are earthquakes that have an impulsive P wave followed by a longer period signal. Here's seismograms for a regular earthquake with a P and an S, and then the mixed frequency earthquake have a P followed by some lower frequency content in following the P train. And you can see it again here in the spectrogram. It's that part that makes it different from the regular earthquakes. Now, if we isolate those using SpecUFX, and then we plot them as a function of time, we can see that here on the left, the regular earthquakes, they're so this the dashed line here, that's the 2015 eruption in April, that there is a normal increase in the number of earthquakes, but compared to the number of earthquakes, the increase in the MFEs is much earlier, much more pronounced than the earthquakes. And so the relative, the ratio between MFEs and earthquakes is really appears to be a precursory signal in this eruption and possibly in the next eruption too. That gives us like a 15-hour alert, or possibly more, because those MFEs actually start a little bit earlier, also less clear. So again, this is a week of data and then and hours of data. And so the spatial pattern of those mixed frequency earthquakes, we can track them in time. And what we find is, so they're here shown in the map view as blue dots. What we find is that they migrate north along the magma chamber, then return and move upwards and essentially end up where we find the erupting lava from the impulsive seafloor events. So the timing and spatial correlation is almost perfect. And so our interpretation of those mixed frequency earthquakes, that they represent cracking of the brittle crust right above the magma chamber, and then magma volatiles moving into those cracks right away. So that's what's causing the lower frequency content right after the P onset. So we have moved this into in our real-time system, which is very similar to the one that we run for California. It's just now on much smaller scale for Axial, and except that here we used machine learning in a real-time process rather than in the California version, where I used the USGS initial locations. And we were going to the whole tasks of discrimination, and then track both earthquakes and MFEs as part of that system. And so this is now closely being watched. The bottom panel shows the ratio between MFEs and earthquakes over here, and compares that to the one in 2015. So we're still far away if that eruption from 2015 is characteristic. Okay, I think I can skip that. So opportunities and challenges. I think I stressed out during my presentation that this is a good time to be a seismologist with the tools and the computational power that we have, and the unsolved problems that we still have in understanding fault structure mechanics and big earthquakes and small earthquakes in general. What the opportunity right now is, what you think is very exciting, is the use of unsupervised machine learning and trying to learn from those huge catalogs and trying to learn about the seismogenic processes that cause those catalogs. The challenge is it's a big data problem, but we have lots of compute powers. But to just give you an idea of the numbers is, so this is Northern California, no machine learning, no template matching, and we get 7-8 billion correlation measurements, 1 million earthquake. And for just a small subset in central Italy in the Amatrice sequence, we have an SGA detector. With a machine learning detector, we get about 10 times more events. And then if we run a cross-correlation detector on that, we get about 25 times more events. So there's an explosive growth of detections and presumably events that we can associate to those detections. So the real problem is I/O. And we still, in those millions of earthquakes, we need to ensure reliability of the catalogs. It's usually I spent more time on that than generating the catalog. And you can do, various things. One part is that you can use the repeating earthquakes to validate your comprehensive catalog in California, for example. So in California, the 95% of the double difference catalog are within 10 meters of the repeaters. That gives also kind of a sense of reliability of those catalogs. Then raise awareness of limitations. I think that's a huge thing we need to figure out, not treating them as point sources. And then dealing with a new generation of called the machine seismologists that are very good at using continuous data streams. But then at the end, we run into problems like this. So that's from the East Pacific rise. That's a almost repeating earthquake source. Those are manually picked by an analyst onset of the P arrival. And you can see that they were picked late over here and then started picking early over here. And what's happening here is a simple P2S conversion mixing with a directed P arrival on the mid-ocean ridge. So those are very short distances. And so if a machine learning, it will be interesting to see what the FaceNet will pick here, whether it will change too from a early to a late. So it's actually mixing a P2S conversion with a direct P arrival. Now for relocation, it doesn't matter that much as long as you be consistent with linking those events together and those, but not across. Anyway, those are details that they will be important to convey to dealing with those new catalogs. And then a very, very ridiculous problem that I run into now is event IDs. I'm used to having event IDs that are stable and robust over time. And now with every machine learning catalog, you get new IDs. And so comparing different catalogs is more difficult than one would think of. And then, well, the main challenge right now is raising money. Thank you.
Felix, thank you. Really a wonderful talk. I will invite people to unmute and turn your camera on if you like. Join me in thanking Felix for a great talk. Lots of things to think about.